Starting time. All right. So last time, just as a quick refresher, just so we can talk about where we were last time. Last time we talked about breaking up a vector r into the time derivative of its vector r. No sponsors today, we don't have time. The time derivative of a vector r into two parts. There's one part which tells us about the change in the magnitude of the vector r. Remember, the r is the position. And the other term tells us about how the direction changes, because it only cares about the way that the unit vector r hat changes. And r hat contains all of the directional information of the vector. So there are two possibilities that we could have, or rather two different ways that a vector r can change. Go away, go away. So let's talk about the two different possible ways that a vector r can change. There we go. So it could be the case that an object whose position is described by r is moving towards or away the origin. So imagine the picture here is you have your coordinate system, you have your vector, and then this is your vector r, and then your vector v is maybe, green does not go well in that. Maybe your vector v points directly towards the origin. In that case, the only thing that's changing is the length, the direction of the resulting position vector at a later time doesn't change. So what that implies is it implies that r hat of t is unchanging, and r of t without the vector symbol is changing. And so in that case, all we have to do is go look at the formula from last time, and we find that the velocity vector is just dr dt r hat. The other option is that the object, why isn't the pen writing? Is that the object is moving in such a way that it never changes its distance from the origin. Why isn't the pen writing? So an example of that type of motion would be motion in a circle, right? Or like if you tie a ball to a string and then you like spin it around your head, the distance that this ball is from the stick or whatever is unchanging. So in that case, r of t is unchanging, but the vector that points from the origin to the object is changing. So in that case, we would have that v, the velocity vector, is the speed r times the rate of change of the position vector. Sorry, of the unit vector, the position unit vector. So this particular scenario would be anytime an object undergoes circular motion, or spherical motion really, but I'll write circular. Because if an object moves on the surface of a circle or on the surface of a sphere, then its distance from the center is always the same. And so this r of t would never be changing. Now, the third possibility, I suppose, is that a particle could, or an object could be moving in a combination of the above two ways. Come on. What? Why did the mail app just, what? Something horrible is happening. What is going on? Technical difficulties. This is not the day for that. Just opened up like the mail app. No, it's just running slow and I don't understand why. Are you going to get another free year of credit monitoring? What? Oh, yes, you are. Okay, so the pen is just not responding. Let me try a different pen. Maybe that'll work. Second pen's not working. Let's try restarting this pen. All right, that's not working. It's recognizing my fingertips. Let me try inverting the tablet. Maybe that'll work. I don't know why that would work, but maybe it would. No, okay. Let me try changing the battery out on my pen. Okay. So this is fun. Sorry, guys. At this rate, this is not going to work. Let's go into tablet mode, see what happens then. Nope, still can't write. I can type, but it's not particularly helpful because I have to be able to write equations. Okay, what I can do, here's an idea. It's annoying because it's not useful for you, but what I can do is I can scroll through my lecture notes and kind of narrate. So I'll do that. I could restart the tablet, but it would take too long. I will just narrate my lecture notes, and that's what we'll have to do. Let me try this one moment. No, the issue is just that the pen's working. It's like freaking out. You can even see it. See? Oh, okay. So I will just use the front camera. And I also just realized that my lecture notes are not on this machine. Sorry for the technical difficulties, everybody. It's annoying, I know. By the way, I'm going to, well, because some people want to watch it live, I'm going to upload the lecture notes now to Canvas, so you can go take a look at them if you want. These are what I planned on going over today, but I might not make it all the way. No, it's just the pen's not working. Like I can't write. Like the pen is just not functioning. So this.ucdavis.edu. I could type, but I can't write equations. That's the trouble. So I have to go download the LaTeX in real time. I did that as an undergrad. It's not fun. I don't know why the machine's running so slow. Yeah, I could do paper, but that seems silly. I'm already here. And I don't have paper on me. No, it's any application. The pen's just not being detected. Today is not my day. That's okay though. Things have been worse, so we'll be okay. We'll survive. So I'll have to apologize because the lecture notes that I'm going to pull up, they're typically what I would upload. They just don't look as good as I would like them to look, but you know, they'll have to do. Oh, I can stop sharing. Let me open it up as a PDF. Come on, downloads. All right. There we go. Lecture notes are pulled up, ready to go. Let's try this again. All right, so you'll have to bear with me because I'm not used to lecturing this way, but it'll do. Okay, so where were we? Yeah, you can see that's running really slowly. Right, so I mentioned that that there's the two possibilities. You could have the case where you have the object is moving either directly towards or away from the origin, or you could have the case where the object is moving kind of in a circle. And so in that case, is there some way to highlight? There, this is what I want. In that case, the speed isn't changing, but the direction is. And so what you'll end up having is the velocity vector is just the position vector times the rate of change of the unit vector, of the unit position vector. Right. So and like I said, you can describe that type of motion as an object moving on any sort of sphere-like surface. Pen's still not working. The light is blinking. I wonder what that means. Well, not going to worry about it now. Right. So it turns out that you can actually categorize the type of motion that we're talking about here. You can kind of give a name to this notion of motion that is going towards or away from the origin, and motion that goes in a circular direction. And in fact, that kind of encapsulates all types of motion. So if we can decompose motion into towards and away from the origin and circular motion, then you're all set. So we have to do a little bit of algebra here to show that this is true. So just as a quick reminder, remember that if you have two vectors and you take their dot product, that involves the cosine of the angle between them, right? And so in particular, if the angle between them is 90 degrees, i.e. they're perpendicular, then that would mean that the cosine of the angle between them is 0, and so the dot product is 0. So that is to say, if A dot B is 0, then those two vectors are perpendicular to each other. That's just a true fact about any sort of vector. Now, what we can do is we can actually see what happens when we take the dot product of r hat with the time derivative of r hat. Now, you might say that this kind of just comes out of nowhere, but the end result of what we get for that dot product is we'll get something that tells us that those two vectors are perpendicular. So let's take that dot product and see what happens. So the dot product of r hat dotted into dr hat dt, all I'm going to do is I'm going to rewrite this as 1/2 times twice that dot product. All I've done is rearrange the order r hat dot dr hat dt plus dr hat dt dot r hat. The order doesn't matter for dot products, so this is fine. I just multiplied by 2, split it up, and then divided by 2. Next step is I realize that r hat dot dr hat dt plus dr hat dt dot r hat, that's just kind of working backwards from the product rule. That's just the time derivative of r hat dot r hat, right? It's the derivative of the first times the second plus the derivative of the second times the first. But we know that r hat dot r hat is just the number 1. Any unit vector dotted with itself is 1. And so we get that the time derivative of 1 is 0, which tells us that that r hat is perpendicular to dr hat dt. And that's using this fact that a dot b, if a dot b is 0, then a and b are perpendicular. So what we learned from that calculation is that the vector dr hat dt, which points in the same direction as the velocity, that vector is perpendicular to the position vector. So in fact, whenever an object is undergoing circular motion, and perhaps this kind of makes sense, the line or the line that connects the center of the circle to the object or to the edge of the circle is perpendicular to the line that travels along the circle. That's perhaps not surprising, but that's really what we're talking about here. Now, using that notion, we can then decompose the two terms. There's one term that's proportional to r hat, this term on the left. That term is just proportional to r hat. It's in the same direction as the position vector. And then there's a term that's proportional to dr hat dt. And as we just established, dr hat dt is perpendicular to the position vector. So what we can write the velocity vector as the perpendicular velocity vector plus the parallel velocity vector plus the perpendicular velocity vector. So the perpendicular velocity vector is just any component of the motion that is not in the direction of the position vector. The parallel velocity vector is just the part of the motion that indicates speeding up or slowing down. Sorry, not speeding up or slowing down. Any that indicates getting closer to or further away from the origin of the system. Now, a lot of what we talked about here, this notion of the position vector and what direction the position vector is relative to the velocity vector, isn't super useful. And the reason I say that is because when you're like solving a real world problem, the origin is not something that's like given to you. It's usually something that you pick. So the vector that points from the origin to the position of the object just isn't particularly like meaningful. Like who cares if the velocity vector is in that same direction? If you had chosen a different origin, it wouldn't point. They wouldn't be in the same direction anymore. So that's kind of, it can be useful, but it's not super useful. How did I get the 1/2 ddt type of r dot r? I just inverted the product rule. So remember the product rule, ddt of f times g is df dg, or sorry, is df dt times g plus f dg dt. Right, it's just the product rule, and I just used it in reverse because derivatives distribute over the product, or over the dot product. Right, but so while the velocity vector, this notion of parallel and perpendicular, isn't so useful, for acceleration it is. So we can do the exact same thing that we did for acceleration. We can break up the velocity vector into the speed and into the direction of the velocity vector, like we did earlier, and then we can write that out using v hat, the direction, and v. And what we get is that the acceleration vector can be written as the speed, or sorry, the magnitude of the change in speed dv dt times in the direction of the original velocity vector plus the speed times the change in direction of the velocity vector. And so here, speed kind of is meaningful. Sorry, velocity kind of is meaningful, whereas the position vector isn't always. So here, this notion of parallel acceleration and perpendicular acceleration does make sense. And we get that this second term is perpendicular to the velocity vector in the same way that we found that this second vector dr hat dt is perpendicular to the position vector. It's the same type of calculation. We're just doing it again. And so so what we capture here is that this first term tells us the part of the acceleration that relates to changes in speed, right? It's literally speeding up or slowing down. If dv dt is positive, then you're speeding up. If dv dt is negative, then you're slowing down. On the other hand, the second term tells us whether or not the object is turning. Now remember, acceleration is just any change in velocity, or it's the time derivative of velocity. But in particular, if the velocity is changing, that means the acceleration isn't zero. But what that can mean is it can mean that the speed isn't changing, but you could be turning around a corner. Because you're turning around a corner, your velocity, which may have been initially forward, is changing to become to the right, which is a change in velocity. It's just not a change in speed. So this second term captures the change in the direction of the velocity. Importantly, that component to the acceleration vector is perpendicular to the velocity. And here's a link, or not a link, it's just an example that I pointed out, 1.6.4 in the LibreText. Practice doing these kinds of things, breaking down acceleration and so on. Is this really, wait a minute, is this actually the most recent version that I have? Oh, it might not be. Oh, no. Oh, no, I think it is. Let me just scroll down really quick just to check to see it's the most recent version. Yeah, it is the most recent version. Okay, right. So with that underway, and I know that seems kind of like it wasn't super useful, it becomes useful here. So let's talk about circular motion. So I'm going to have to describe this drawing rather than draw it for you real time. Sorry about that. Is the pen working yet? No, I'm going to have to fix that later. So we're going to continue a special case of motion. And this is a relatively common special case. It's just an object that's moving in a circle. You can consider like you tie a string to a rock and then you swing the rock around. That rock undergoes circular motion. Like a carousel undergoes circular motion. Circular motion's everywhere. So what we can do is we can think about what ways the velocity changes when an object is undergoing circular motion. So let's imagine that an object is starting off at a position vi. Sorry, at a position at the base of this vector vi, right? And it's going to be traveling in this circle counterclockwise. So initially, it's going up and to the left along this rightmost red vector. That vector is we're just going to call it v sub I with a vector. It points in a direction. In particular, it points in the direction that's perpendicular to the, or sorry, that's parallel to the or tangent to the circle, and it has some magnitude. At a later point in time, vf, maybe a second later, its velocity points in a different direction, and its speed may or may not have changed. But let's, for the sake of this diagram, let's assume its speed isn't changing. It's just going around the circle at a constant rate. Well, how would we find the acceleration vector? How would we figure out what direction it points in and what its magnitude is? Well, this is an approximation, but what you can do is you can just find the difference between the final velocity vector and the initial velocity vector, and then just divide by how long it took to go from point A to point B. This is technically the average acceleration vector, but as the time duration gets smaller, the velocity or the average acceleration gets closer to the instantaneous acceleration. So this is a fine approximation. So what I'm going to do is I'm going to take this VI and I'm just going to move its base over to the middle point between VF and VI. And then I'm going to draw it. So there's the vector VI. And then I'm going to do the same thing with VF. I'm going to move it back to the middle point. The reason I'm putting it in the middle, by the way, is because the acceleration vector should, the average acceleration vector should be pretty close to the instantaneous acceleration vector between the initial and final times. It's a little bit of an aside, but it's not super important. So we drag those two over, and then we can actually just do the subtraction of the vectors. VF minus VI would be formed as this green vector, and then I'm going to take that vector and put it back at the base. So you'll see that that average acceleration vector points straight down, straight towards the center of the circle. And you'd find that the acceleration vector at any point along the circle indeed does point towards the center. And that's why this type of motion is called centripetal motion, not centrifugal. Important distinction. We won't actually talk about what centrifugal motion is at all. It's because it's not super important anymore. But it's centripetal acceleration. So an object which is always accelerating towards the center of a circle undergoes centripetal acceleration. Centripetal meaning center seeking. So the name kind of makes sense. So in fact, anytime the acceleration of an object points towards a certain point, like a particular point in space, like say the center of a circle, that object will undergo circular motion. That just is true. And we'll derive that later. Right, so suppose that instead the speed was changing, then things can get a little bit more complicated, right? Because you could have part of your acceleration that involves the change in speed of your, or the change in speed, that part of your acceleration, that would point in the same direction as the velocity vector. And then you have the centripetal part that points perpendicular to the velocity vector. So all I've displayed here is the case where the speed isn't changing, where this dv dt is 0. And that's why the acceleration vector that I drew, or rather the average acceleration vector that I drew, is indeed perpendicular to the velocity vector. If, on the other hand, the object was speeding up as it went in a circle, then you would have a component of your acceleration vector that points towards the center. That would still be described by the centripetal acceleration. And then you would also have a component of your acceleration vector that points along the velocity vector. And that would indicate the change in speed. So the thing to imagine here is, imagine you're going around in a circle, maybe you're driving in a circle on a car, but you're slowly putting your foot harder and harder on the gas. So you're speeding up, but you're also accelerating towards the center of the circle because you're turning. Now, you guys might, I'm curious if you would know what would happen if you slowly sped up as you went around the circle. What would you feel? Would you feel like you're getting flung at the same, like you know how when you're taking a turn, right? Like you kind of driving along, you turn the car, you go like that, and so on and so forth, right? So the question is how much? Yeah, you would slide out. But the question is what would you feel as your acceleration or as your speed increases? Would you feel more and more pushed to the side, or would it be the same amount, or would it be less? So I suspect, yeah, everybody's saying more. Yeah, so you feel more and more feel like you're being pushed over to the side. And that's because the acceleration, the reason why you're pushed over to the side is because of this perpendicular component of the acceleration. It's the centripetal acceleration that's doing that to you. And so your intuition agrees. It says that if you're moving faster around a circle, your centripetal acceleration should be bigger. So what can we actually say about the centripetal acceleration? By the way, sometimes we'll call centripetal acceleration a sub c. It's just the perpendicular component of acceleration, though. So just be careful. Yeah, so what can we say about the centripetal acceleration? Well, we know that if you go faster around a circle, you feel more acceleration. Your acceleration increases as your speed increases. In particular, they are related by some relationship. If one goes up, the other goes up. What happens if you were to drive at a fixed speed, but go around a really small circle? Would you feel more or less push than if you were to drive at a speed around a really large circle? Would you feel, yeah, you would feel more push. And that's because the circle's tighter, right, in a sense. And so it's also true that if the object goes about a smaller circle, you also have a larger centripetal acceleration. The idea here is that for every like quarter turn, or every eighth of a turn, or every however much of a turn, the smaller the circle, the less time you have to make that turn at a fixed speed. So your center-seeking acceleration, your centripetal acceleration has to be larger. Similarly, if your velocity is higher, then you have less time to make that turn. So again, your centripetal acceleration has to be larger. So in fact, those two relationships alone get us to a formula for the centripetal acceleration. We can actually write that the centripetal acceleration, or rather the magnitude of the centripetal acceleration, is just the square of the velocity divided by the radius of the circle. So let's just check our intuition. If the velocity increases, then the square of the velocity increases, so the centripetal acceleration increases. Check mark there. If the radius of the circle decreases, then again, the magnitude of the centripetal acceleration increases. So again, that checks with our intuition. So this is a formula. Rarely will I actually ask you to memorize something, but this is a formula that you guys should definitely remember. It shows up so much, and it's so useful to just kind of like have it stored in the back of your head at all times, that this is something that you should like 100% remember. And honestly, you'll get enough practice with it that you'll memorize it even if you don't intend to. But I just want to say that this is something that you should have in your memory, given enough time. Right, so there's an example of calculating centripetal acceleration that I can link to. I'm not going to click on this because we don't have a whole lot of time, but no, you can't. So no, you wouldn't be able to. You might be able to derive it if you're extra clever with your calculus and so on, but it's not particularly straightforward to get just from kinematic equations. No, you would need to be able to describe circular motion in terms of you would need to use radial or polar coordinates effectively, and then say that, and then write your you'd have to relate the rate at which you go around a circle to your speed and so on and so forth. It's like we can talk about that later, and we can actually go over that at some point if anybody wants to, but it's not something that you guys would know off the top of your head necessarily. R is the radius of the circle here. Yeah, the circle that the objects go around. Right. So like I mentioned, like a merry-go-round, circular motion isn't always just the result of something moving in a circle, right? Sometimes it's just a result of something spinning, like a merry-go-round, or a there's another name for it. You know what I'm talking about, though, hopefully. So the question is carousel. Thank you. So the question is when you describe the motion of, say, carousel or merry-go-round or a bike wheel or a car's wheel or whatever, what you do is you describe it as how many RPMs, how many rotations does it go per minute, or maybe you describe maybe if you're feeling extra fancy, radians per second or something. Really, we actually would prefer to use radians per second. That's the most natural choice. But you can also convert between the rate at which an object is spinning and a rate at which the edge is moving, like how fast in meters per second is the edge actually moving. That's a thing that you can do. You can convert, say, rotations per minute to linear velocity. When I say linear velocity, by the way, what I mean is something with units of minutes per second, or of meters per second. Yeah, and Eli, not everybody knows that. That's why I'm going over it. That's all. So first, let's talk about, okay, so one rotation per minute. If you could figure out how far the edge traveled in that 1 minute, then you could just divide that distance by a minute, and that would give you the linear velocity, right? So we need to know how to convert the amount of rotations a thing does in 1 minute to the distance that the edge of that circle traveled. So let's draw a picture. So here's a circle, and say that you have an object on the edge of the circle. Circle is radius r. Let's say the object starts off down here, and then it travels a distance s along the surface, or along the circle. So the question is how many, like what fraction of a rotation did that object travel? Well, we can figure that out using geometry. First, we have to note that a full rotation is 2 pi r distance, right? The circumference of a circle is 2 pi r. So the distance that the edge travels for one rotation is 2 pi r. Now, just as a reminder, there are 2 pi radians in a full rotation. So you might say, oh, that 2 pi there, that looks awfully like it belongs right there. And you'd be right. If an object only traveled pi radians around the circle, then it would only travel a distance of pi r. Indeed, the principle is generally true. The distance traveled along the edge of a circle is the radius of that circle times the number, or the amount of radians that object traveled through. So if it went through pi radians, then the distance is pi r. That's the distance that the object travels. If it went one full revolution, i.e. 2 pi radians, then the distance is 2 pi r. If it went 4 revolutions, the distance would be 8 pi r, because 4 revolutions is 8 pi radians, and so on. Now, keep in mind, for the majority of this course, we're going to be using radians, so please get used to it. It's like very much a pain to deal with degrees, especially when you're not sure what the question is asking in. So make sure that you just kind of stick to radians. It'll make your life easier, with some exceptions. All right. So once we know how to get distance covered, now all we have to do is divide the distance by a time to get speed, right? So if an object, say, travels a distance s in a duration delta t, then the speed would be s divided by delta t. And so we could figure out if, say, it traveled 2 pi r rotations, sorry, if it traveled 2 pi r units of distance, one full rotation per second, then the speed would be 2 pi r divided by the duration. So we can actually do this kind of formally, mathematically. Remember that speed is just the rate at which, it is the rate of change of distance covered, right? So if you cover 5 meters, or if you cover 5 meters every second, then your speed is 5 meters per second. And that's because the distance covered, the function that describes your distance covered, would be something like 5 meters per second times t. So a time derivative of that would give you 5 meters per second. Now we know how far an object travels along the edge of a circle, right? We just derived that. If you travel an angle, if you do theta radians of rotation, then we know how to rewrite your distance traveled along the edge of the circle, s, in terms of your angular travel and the radius of the circle. In particular, just substitute s for r theta, that's our formula. And we get that the velocity is the time derivative of r times theta. Now, r is just a constant, it's just a number, it's the radius of the circle. So that gets pulled out of the derivative, and we're left with r times d theta dt. Now, theta tells you the amount of degrees, or the amount of radians that you've covered. In this case, it actually has to be radians, otherwise it doesn't work. So it's the amount of radians that you have covered, that you have rotated by. And so the rate at which you're rotating, the rate of change of the amount of radians that you have rotated by, you could think of theta as a function of time, starts off at 0 and then it increases with time as you rotate further and further. The rate of change is something that we call the angular speed. It's the rate of change of theta, and the letter that we use for it is a Greek letter, and we use the letter omega. It looks like a little w, but it's rounder. So it's this little guy. So you can write the linear speed around a circle in terms of the angular speed, which tells you how many time, or which is a way of telling you how quickly you revolve around the circle, times the radius. And so using that formula, we can actually re-express the centripetal acceleration using angular speed rather than just linear speed. Sometimes this is useful, by the way, because sometimes you're not given something like sometimes, like, for example, if a carousel goes around at, I don't know, two revolutions per minute, that doesn't tell you what v is. That tells you how long it is to go around one loop. So you would want to use the angular speed version of its centripetal acceleration there because it's more useful. S equals r theta. So this is just a generalization. That is literally just the formula for arc length in a circle. So if you do want a refresher, one thing that you could Google is arc length of a circle, and that will probably show you how to derive it in a more elaborative way than I have here. This is just supposed to be a refresher, hopefully. Right, so we can write the centripetal acceleration as r omega squared, where omega is just the angular speed. Now, just to keep everything on the straight and narrow, omega has units of radians per second. Radians don't typically have units, so really you might write this as 1 per second or as inverse seconds, but I like to write the word rad, R-A-D, in the numerator just to remind myself that I'm talking about radians per second and not hertz, which is inverse seconds, because a radian is different from 1. It's just a number though. All right, so there's an example of this type of calculation, not necessarily merry-go-round, but there's an example that I linked to here, which shall be useful in the future. All right, so we're going to talk about circular motion a lot more in the future, and it's going to come up a lot, but that's basically all there is to it. You know, you can get more complicated, but for the most part, this is what you need to know. You need to know how centripetal acceleration relates to speed, relates to angular speed, and so on and so forth. All right, let's talk about projectile motion, which you probably have all seen in high school, I hope. So like the centripetal, or like circular motion, projectile motion is just a specific case of general motion, you know, motion in every which way. Projectile motion is the case of motion where you have a single component of your velocity changing. And typically, we ensure that that velocity is changing by a constant amount. The acceleration in that direction is constant. What this means is that the acceleration is only pointing in one direction. Your acceleration vector isn't changing direction. Your acceleration vector is constant and in a single direction. So anything that has constant vector acceleration technically undergoes projectile motion. So the most obvious example is free fall. Now we've already talked about free fall. It's just the property, or it's the state of motion when an object is just falling under the influence of gravity. And the reason why that is classified as projectile motion is because the acceleration vector has magnitude g, and it points downward. So the acceleration vector is just a constant. It's if plus y is up, then the acceleration vector would be negative g y hat, or sorry, negative g j hat. And the reason why we call that projectile motion is because if an object is moving horizontally while it's falling, like if you shoot a bullet horizontally, the horizontal component of the motion, like the speed in the horizontal direction, cares zero amount. It cares not at all about what's happening to the component of the motion that's vertical. That is to say, the acceleration only affects the motion in the direction that the acceleration points in. So projectile motion is just basically free fall, but with motion but with additional terms that are unaffected by the free fall motion. So think, for example, that you fire a bullet to the right. Let's say the right is the positive x direction and up is the positive y direction. So there would be a component of the velocity that is in the x direction, and there would be a component of the velocity in the y direction. Now, the component of the velocity in the x direction can only change if there's an acceleration in the x direction. But because we're assuming that, you know, it's just gravity, then the only component to the acceleration is in the y direction. And so that will only affect the y component of the velocity. So let me explain with equations here. So as I said, typically if we choose the plus y direction to be up, and we're talking about free fall, g with under the influence of gravity, then our acceleration vector is negative g, remember g is just a number, in the j hat direction. So then we ask the question, what exactly is the velocity as a function of time? And remember, it's a vector, so it's changing with time, and it's changing its direction as well. And that kind of makes sense. If you shoot a bullet horizontally, it'll start off going this way, but at a later time, it'll be arcing down, right? Because it'll arc like that. So its velocity, like the magnitude and direction of the velocity vector change. Now, the time derivative of the velocity is, by definition, acceleration, right? And so what we can do is we can use that expression, the definition of acceleration, to relate, to find the acceleration in the x direction and the acceleration in the y direction. In particular, in the x direction, that would just be the x component of the acceleration. But we know the acceleration only points in the y direction. So this is just 0. There is no I hat component. Whereas the acceleration in the y direction, well, that is just the y component of the acceleration, which is just negative g, again, from looking at our formula for the acceleration of the acceleration in free fall. And so what we can do then is we can just integrate these formula. Remember how we went from acceleration, we went from dv dt equals a, and then we integrated that to figure out what v of t is. We can do the same thing. All we have to do is integrate these two equations, and that will give us vx and vy. So v, which is vx of t in the I hat direction, and vy of t in the j hat direction. By the way, I know we're out of time, but I did say we would go over. Then all you do is integrate. So because the acceleration is 0 in the x direction, our velocity is just the initial velocity in the x direction. Our velocity in the y direction, well, we have to integrate a minus g. So we get a factor of t, because if you integrate minus g with respect to t, you get minus gt. And then we have our constant term, which is our velocity, our initial velocity in the y direction. So this tells us how the velocity changes with time. The velocity in the horizontal direction is unchanged, and the velocity in the vertical direction does change. It changes by negative g every second. And then we can integrate this again to find the position as a function of time. So again, we would integrate vx of t. This is because the time derivative of position is velocity. So you would integrate vx of t to find the x component of position. And that would be v naught x times t, because this is a constant here, plus the initial x position. And then we would integrate the y velocity to get the y position. We would integrate minus gt, so that's minus 1/2 gt squared, plus v naught y t, because this is a constant. And then we have the initial y position. V sub o, so v sub o means initial speed. So v sub o comma x, that means initial speed in the x direction, or rather initial velocity in the x direction. It's the x component of the initial velocity. Take care. So if you're given the initial velocity, if you're given the initial position, you can just figure out where the object will be at any later time. So that's actually kind of powerful, right? Because it means that you can predict where something will go just by knowing what it started doing, like what its initial velocity and its initial position were. So I mean, already that's physics, right? Like figuring out where things will be based off of where they started. But sometimes problems are more complicated. Like, for example, what if instead of being given the initial velocity in each of the two components and then the initial position, what if you're given the initial position, but you're only told the only information you're given about the velocity is the speed and an angle? Maybe it's the angle above the horizontal axis. Well, then you could find out that initial velocity information by just drawing a picture, right? Your initial velocity points up and to the right, say at 30 degrees, and maybe it has a magnitude of 5 meters per second, and then you can just use trig to figure it out. So for example, you could find that the cosine of 30 degrees is equal to the horizontal component. I don't know why this isn't there. It's not showing up in my lecture notes, but it'd be equal to the horizontal component of this vector, v naught in the x direction, divided by the length, divided by the hypotenuse, right? SOHCAHTOA, so cosine is adjacent over hypotenuse. So it would be the x component divided by the hypotenuse, 5 meters per second. And then you could solve for v naught x. So v naught x would be 5 meters per second times cosine of 30 degrees. And you could do the same thing for the vertical component. Now, I'm kind of just going to outline some steps if you wanted to generally solve a projectile motion problem. And by the way, projectile motion problems can generally have a lot of variables, and they can have a lot of initial data given. So you kind of have to use creative thinking, but this is generally how you should approach it. So you start by just drawing a picture. That's really what you should do for every physics problem. You should always draw a picture and label it Just that way, then you can kind of get it out in front of you, so you know what you're doing. And then, no, people don't say this enough, but actually think about what's happening. Like, try to understand what your intuition says should be happening, so that you can kind of follow your nose. So after you've drawn it and thought about it, whatever problem you're trying to solve, you're going to want to pick an XY origin, like some origin of your XY coordinate axis. So usually that might be where the object started, but maybe that will just be some other random place. It doesn't matter what your XY coordinate axis is or where your origin is, but you got to pick it. And then you just have to work with it and be consistent. You should also make sure that you pick your X and Y directions appropriately. X doesn't always have to point to the right. Y doesn't always have to point up. Sometimes it'd be useful to have X pointing up and to the right and Y pointing up and to the left. That's equally valid. As long as they're perpendicular, any choice is okay. It's just you have to be consistent, and you have to make sure that you know what you mean. Third thing to do is, if it's given, find what the components of the initial velocity are. Maybe you're just given the initial components, in which case you don't have to do any work. But maybe you were just given a magnitude and a direction, in which case you have to do some trigonometry to figure out the components of the initial velocity. And maybe, in fact, maybe even that information isn't given, but maybe you're trying to solve for an angle, for example. In that case, you would just let your angle be, say, theta, and then you would write out what your components would be if the object was traveling at that angle. So, like, instead of, say, 30 degrees, what if the object was traveling theta radians above the horizontal? Then the velocity vector in this case would be 5 meters per second times cosine of theta. That'd be the x component, and the y component would be 5 meters per second times sine of theta. And then wherever you would see v naught x or v naught y, you would just plug in that formula, the appropriate formula. So at that point, you kind of set up everything. Like, you have all of your information, and now you just have to go and solve. So the next step is literally just write down the equations of motion. So when I say equations of motion, what I'm really talking about are the equations that look like this. Now, it won't always be those equations. In particular, if the acceleration isn't straight down, like, let's say the acceleration, maybe you're on some weird planet where the gravity points down into the left, or down into the right, I suppose. Well, then your acceleration vector is different. It's still technically projectile motion because the acceleration vector is constant, but it's pointing in a different direction. So you'd have to figure out what the new equations of motion are. But again, it's not that hard. It's just what the equations of motion are, just actually, we even talked about it on Friday. It's the initial position plus the initial velocity times time plus 1/2 times time squared times the acceleration vector. And then you can break it up into components. Can you find the angle and then the x, y, and x components? What if I mean, you could do that, but yeah, you could precisely do that. Yeah. And then you just have to write down new equations of motion, because these that I wrote down only involved acceleration that's downwards. But in general, you can have acceleration that's in any which direction, and your equations of motion would change accordingly. This term would be different, the term that's proportional to t squared. Right. A useful tool that you guys should do, make sure that you note what quantities you know, like which things are given, and then also write down the things that you're trying to find, because it's useful to keep those things in mind. Step 5 is, hopefully at this point, you just have a system of equations, and you have a set of knowns and a set of unknowns, and then you just solve. And it's just some algebra at that point. And then maybe you rewrite your answer in terms of a vector if you need to. And then obviously, as a last step, and everybody should always be doing this, check to make sure that your answer makes sense. Like, if the question is, a cannonball is fired off at t = 0, and it's fired at 45 degrees above the horizontal at 300 meters per second, and how long does it take to hit the ground? If you get a negative answer, probably not a sensible answer, because it should hit the ground at a time later than when it was launched, right? So, you have to check those kinds of things. So this business about the range finding equation, it's talked about in LibreText. It's a useful equation. Basically, it tells you if a thing is fired from ground level at some angle theta and at some initial speed v naught, the question is, how far does it go before it hits the ground? It's this formula. You can derive it, and I challenge you to derive it, actually. It can be handy, but I wouldn't memorize this. I would figure out where it comes from. I'm not going to go over it, but it is in the LibreText. And then there's a whole bunch of examples for practice for projectile motion problems. And you can find these everywhere. If you really need more practice, Google projectile motion example problem, and you'll find more. There's going to be millions. So that takes us through to the end of where, not where I wanted to go, but that's as far as we got. So we'll have to continue more on Friday, and we'll end here.